Hello and welcome. We see lines literally everywhere, but have you ever stopped to think about what happens when they meet? Or maybe even more interesting, when they don't? Today, we're diving into the simple but honestly profound rules of geometry that control every single intersection. There are some serious secrets hiding in plain sight. Just think about this for a second. Go grab a piece of paper and just fold it. That crease you just made? That's a perfect straight line. Now fold it again, anywhere you want. You've just created a second line that crosses the first. And right there, in that simple action, you're holding all the fundamental principles we're going to unlock today. So, first things first, let's look at the most basic interaction there is. What happens when two straight lines cross each other on a flat surface, like a piece of paper? It seems almost too simple, right? But underneath, there's this really cool, predictable, almost magical logic going on. Okay, so here's a little challenge for you. Look at this intersection. We've got four angles. Now, I'm going to tell you that just one of them is 120 degrees. The question is, can you figure out the other three without a single measurement? Go on, you can pause and think about it for a sec, because the answer is hiding in one simple fact about a straight line. All right, let's break it down. The key is that a straight line is always 180 degrees. So look at step one. Angles A and B are sitting together on a straight line. If A is 120, then B has got to be 60 to make it 180. Simple as that. And from there, it's like a domino effect. Now look at B and C. They also make a straight line. So if B is 60, C has to be 120. And finally, C and D form one last straight line, so D must be 60. And just like that, we've solved the whole thing. So that little trick we just figured out, it actually has a name. Look at angle A and angle C. They're directly opposite each other, and hey, look at that. They're both 120 degrees. These are called vertically opposite angles, and they are always equal. Same thing for B and D. This isn't some happy accident. Nope, it's a fundamental rule baked right into the DNA of geometry. And the other tool we use to crack that puzzle is this, the linear pair. Any two angles that are neighbors on a straight line, like A and B were, will always add up to 180 degrees. You get these two ideas, vertically opposite angles and linear pairs, and you've basically got the keys to the kingdom for any puzzle with crossing lines. Now, you might be thinking, if I actually drew this and measured it, I might get 121 degrees or 59. And you'd probably be right. Why? Because real-world pencil lines have thickness, and our tools aren't perfect. This is what our source material gets at. Geometry isn't really about measuring the messy physical world. It's about using pure reason to find absolute, undeniable certainty. Okay, so we've covered what happens when lines cross. Let's level up. On any flat plane, two lines basically have one of two destinies. They can have a very, very special kind of meeting, or they can be fated to never, ever meet at all. Let's talk about that first destiny, the special meeting. When two lines intersect and form four perfectly equal angles, each one has to be a crisp 90-degree right angle. We call these perpendicular lines. Just think of the corner of a book or where the wall meets the floor. That's what we're talking about. And here it is, laid out side by side. The two big possibilities. On one side, you've got parallel lines, kind of like railroad tracks, right? They just keep going, always the same distance apart, forever. And on the other, you've got perpendicular lines. They meet just once, and bam, a perfect four-way 90-degree intersection. Two totally different relationships. Right. So, parallel lines. We get the concept. But this brings up a really big problem, a huge logical puzzle. How can we ever be sure two lines are truly parallel? We can't just trust our eyes. We need a test, a tool that can give us absolute proof. I mean, really, this is the million-dollar question, right? The definition says they never meet, but you can't just, fly along them for a few billion miles to see if they eventually bump into each other. That's impossible. So how do we get that geometric certainty we were just talking about? Well, the answer, our secret weapon, is something called a transversal. It's really just a fancy name for a third line that comes in and cuts across the two lines we're trying to figure out. Think of this line as our detective. It's going to go in and find the clues for us. And check this out. That one single line slices through and suddenly, boom, we've got 8 different angles to work with. The answer we're looking for, the proof of whether those first two lines are parallel or not, is hiding somewhere in the relationships between these 8 angles. Okay, to find that proof, we need to start comparing the angles at the top intersection with the angles at the bottom one. We're looking for what are called corresponding angles. They're the ones in the exact same spot at each intersection. So you look at the angle in the top left corner of the first intersection, and then you look at the angle in the exact same spot, the top left, of the second intersection. Those two are a pair. And this right here is the moment of truth. This is the test. If, and this is the whole secret, if any pair of those corresponding angles are equal, then the lines have to be parallel. Period. It's a done deal. Always. You don't have to check infinity, you just have to check the angles. Okay, so now we have these awesome, powerful rules. Let's actually put them to work. We can basically become geometry detectives now, finding all the missing pieces of the puzzle just by using these relationships. And here's another awesome relationship that pops up when lines are parallel: alternate angles. These are the ones on opposite sides of the transversal, kind of tucked in between the two parallel lines. And guess what? They're always equal too. And why? Because one of them is vertically opposite to the other's corresponding angle. See? It's all one beautiful logical system. All right, puzzle time. In this picture, we are told for a fact that lines L and M are parallel. We also know that angle 3 is 50 degrees. So using our new rules, what is angle 6? This is a classic geometry puzzle, so let's walk through it. We can solve this with nothing but logic. First off, look at angle 2 and angle 3. They're sitting on a straight line, right? That's a linear pair, so they have to add up to 180. If angle 3 is 50, then angle 2 has to be 130. Now look at angle 2 and angle 6. See how they're in the same spot at each intersection? They're corresponding angles. And since we know the lines are parallel, we know corresponding angles are equal. So what does that mean? It means angle 6 has to be 130 degrees too. Done. No measuring, no guessing, just pure logic. So we've built this amazing logical system that gives us certainty. But why do we even need it? Why is it so important? Well, because as you're about to find out, you just can't always trust your own eyes. Okay, I want you to look really closely at this image. Seriously, your brain is an amazing pattern-finding machine. But what is it telling you right now? Do those long horizontal lines look parallel to you? To me, they look like they're bowing outwards in the middle. I know what your brain is screaming, but they are perfectly straight and perfectly parallel. You could take a ruler to your screen right now and prove it. It's a classic optical illusion. All those little diagonal lines are basically scrambling the signals your brain uses to judge angles, creating this powerful illusion that the main lines are bent. And this right here is why geometry matters so much. Our perception is flawed. It can be tricked, but the rules of geometry, they don't get tricked. They give us a system, a language of pure logic to find the real truth, especially when our own senses fail us. It really makes you wonder, doesn't it? What other truths are out there, just waiting for us to find the right way to prove them?